Welcome to Experiment 4. In this lab, we're going to be looking at some potentiometric titrations. They differ from colorimetric titrations in that there is no visual indication of an endpoint. What's really nice about a potentiometric titration is we can visualize the entire titration curve regardless of what the solution looks like. We do this by measuring the pH against the volume of the titrant added. In this experiment, we'll be investigating a variety of acids and bases of assorted strengths, as well as how a buffer is affected by pH changes. Let's get started. To give you a brief overview of this experiment, you're going to complete 4 titrations in total. The first, you'll titrate a strong acid against a strong base, that's hydrochloric acid and sodium hydroxide. Then you'll titrate a weak acid against a strong base, acetic acid versus sodium hydroxide. Then you'll prepare in part C an acetate buffer. In part D, you'll use that buffer and titrate it against the strong base of sodium hydroxide. Then in part E, you'll titrate a weak acid against a weak base, that's acetic acid versus ammonium hydroxide, and compare the curves of each titration. Before we can begin our potentiometric titrations, we first have to calibrate our pH probe. It's how we're going to measure pH throughout the reaction. So you'll take one of these probes and attach it to one of these pH meters. If it's not set to the pH mode, just hit the mode button a few times until you find the right setting. Now we need to tell the meter what value a certain pH is. So we can use 2 buffer solutions with a known pH to set up a calibration curve first. So what I'll do is I'll give the probe a quick wash with some DI water, stick it into my first calibration solution, wait until that reading steadies, then hold cal for just a moment until it beeps and tells me it's okay. Then I'll rinse the probe off, put it into my other pH solution, and this should be about pH 7 this time. Hit cal again and tell the probe that is exactly pH 7 in that solution. So now with a 2-point calibration, we're ready to go for our experiment. A quick forward about the setup of a potentiometric titration. It differs slightly from our colorimetric titration because we use a beaker instead of a conical flask for a couple of reasons. One is we're not swirling by hand anymore, so we don't have to worry about spills too much. And the second is we need to accommodate for our pH probe to sit in the solution as well. So the tip of the probe needs to be completely immersed by liquid. That's why we have inside the beaker both 25 mils of our acid solution and 75 mils of water to make sure the tip of the probe is covered. There's also a magnetic stirrer in there that you can see once I turn it on, starts to spin, and the rest of the setup is essentially the same for our titration. We want to make sure that we can turn that tap without any other interference. And it's very important when this magnetic stirrer bar is spinning that it does not hit the tip of this pH probe because it is glass and could break. Here you can see a demonstration of a potentiometric titration setup for monitoring the reaction between a strong acid and a strong base. On the right, the close-up of the pH meter will allow you to read the pH measurements during the titration. The overlay shows a real-time graph of the titration data, and you may have noticed that there's already a data point on the plot. This represents the starting conditions for the reaction before any of the titrant has been added. In this case, it's on the low end of the pH scale, which means the solution is acidic. The first few additions are rather large volumes, somewhere in the order of 5 milliliters. However, we only see a very small change in the pH. We're most interested about the data around the equivalence point, where the titration curve begins to increase its slope until it's essentially vertical. It's important to capture as many data points around this near vertical portion to obtain the most accurate equivalence point. The volumes being added for each measurement have now decreased as the slope begins to increase. Keep an eye on the data for when these smaller additions have a larger change in the pH, resulting in a steeper slope. You likely won't be plotting the data as you collect it, so what you're looking for is a larger change in pH relative to the volume additions. And there it is. The slope increased significantly. As soon as this happens, slow your titrant additions down to 0.1 milliliter increments, as this is the critical region of data collection. You should notice that the slope of the leading measurements is increasing continuously until you reach a critical point, where a very small volume change leads to a huge change in pH. It should be mentioned that the pH meter must be allowed a few seconds after each addition of titrant before reading a measurement. This is to give the solution time to mix and react properly to produce a more representative pH reading. A pause after each addition somewhere in the order of 3 to 5 seconds is sufficient. There. The small additions of titrant have yielded very large spikes in the pH readings. Once completed, the middle of this near vertical portion of the graph will be the equivalence point. Once you reach the upper portions of the pH region, you'll notice the data slope begins to flatten out again as the reaction proceeds towards an excess of base. Once there is a small change in the pH between additions, feel free to increase the size of the addition volumes. When you do your own titrations, you may notice differences in the shape of the plot, such as a lower or higher pH at the start or end, or that much more or less titrant may be required to reach the equivalence point. Try to think critically about why such features might arise. As a quick note, the pH meters will shut off to conserve batteries. When they start to beep, you can press the up or down arrow to keep them on. If they do turn off, simply hit the on-off button again and resume measurements. There's no need to recalibrate. When finding the equivalence point, do not use the data point collected closest to the center. Instead, measure to the center of the vertical portion of the plot, rule a horizontal line, and read off the corresponding pH value from the y-axis.
Now that you've seen how to perform a potentiometric titration, you can try your hand at a few of your own. Make sure you pay attention to the details in your lab book because there are different volume increments for different potentiometric titrations. Thanks for watching.